Hello
Hello,
everyone,
can you
I'm
hear us?
Seonjin. I'm currently working as a postdoc at Georgia Tech. I'm very honored to attend today's panel discussion as a moderator. Thank Professor Heron for giving me this great opportunity. In this session, we are going to discuss about the challenges and opportunities of GPUs in the future with our panelists, 5 panelists. We have 5 panelists from both industry and academia. Dr. Bradford Beckmann from AMD Research, and Professor John Kim from KAIST, and Professor Dong Lee from University of California, Merced, and 2 other Professor Yifan from College of William Mary, and Professor Daniel Wong from University of California, Riverside. Before we deep dive into our discussion topics, could each of you introduce yourselves and share your first experience you work with GPU from lab to right? So I'll be first. Yes.
Okay. Yeah. So my name is Bradford Beckmann. As you mentioned, from AMD Research and Advanced Development. Actually based out of Bellevue, Washington. Been at AMD for 17 years, so quite a while, and probably the last 12 to maybe even 14 years I've been involved with GPUs. My initial experience with GPUs is a bit unique. Unlike most people who I think, in classes, when you learn about GPUs, you first learn to program them, and then maybe you learn about the microarchitecture. I actually learned about the microarchitecture first. I was privileged to be involved with some meetings that we, right after the merger of ATI and AMD, and when we first discussed, how we were going to build our APUs. And so I learned about the GPU hardware from, legends like Mark Leather and Mike Manter. So a little bit unique than most.
Thanks.
So my name is John Kim. I'm a faculty at KAIST in Korea. Been there for about 15 years. I think the first experience with GPUs, I don't think that's a fair question. I think that's like asking how old you are, because your first experience is with let's say an Ampere or Volta, it means you're kind of young. It fits like a Pascal or Fermi. I think that sort of gives away your age. I think mine goes back a little further, because I think everyone's first experience often is in their parallel architecture class. That was the case for me, but it was through a language called Brook GPU. And if you've heard of that, that's sort of the predecessor. Ian Buck was a T, I think, sort of helping out. So that sort of gives you an experience, a background in terms of what my first experience was. And obviously things have changed quite a bit since then.
My name is Dong Lee. I'm a professor at UC Merced. I work on high performance computing. Before I joined UC Merced, I was a research scientist at Oak Ridge National Lab. So, HPC is among one of the early research fields that adopted the CUDA and the GPU for programming and accelerating those scientific workloads. And I started learn that back in 2007, 2008. And that time, a lot of HPC applications start to use GPU and get 100 times speed up, and people, show their very impressive data in the paper, and I totally got attracted. I was thinking what's happening over there. Maybe I should learn. Maybe that will be useful for my job hunting in the future. So I started to learn GPU at that time. Basically in 2007, 2008. Yeah, it's very useful. It turned out to be very useful for job hunting.
Can you hear me?
I can hear you. Can you hear us?
Yes, I can hear you.
Yes. All right.
And you can go ahead.
I go first. All right. I'm Daniel Wong. I'm an associate professor in electrical computer engineering at the University of California, Riverside. Besides video games in high school, right? The first time I was cognizant that you could program GPUs was probably my computer graphics course. We had someone who worked at DreamWorks come in and teach our class, and I got introduced to RenderMan, a shader language. So that was probably the first time where I realized, hey, you can actually do computational programming on GPUs. And then, after that, I did my PhD and then got into CUDA and everything else after. Yeah.
Okay, so I'm Yifan Sun. I'm a assistant professor at the William Mary. So I first started GPU starting in 2013 because my advisor works on GPU. And I actually not started programming GPUs on real GPUs, but I actually started programming GPUs on multi-to-sim simulator.
Right. Thank you for sharing your first experience with GPUs. Now I would like to ask our panelists about the future of GPU hardware and features. As distant GPUs are adding tensor cores and ray tracing unit to accelerate certain operators. So what types of hardware units do you think could be added to future GPU, or what kind of features do you think will be introduced in GPU? So, Dr. Brad, you.
Oh, we need to go in order?
Sorry.
Well, I'll just be really quick. I mean, I think, you know, we see the mass explosion of distributed computing with GPUs and hardware features that can make that faster. Communicating with networking is, I think, a big area.
I think that's a very difficult question to answer, but I think anything that can make it cheaper and affordable, I think would be something that would really make it more accessible. I think the cost in terms of trying to get access to a GPU these days are just ridiculous. So anything that could help with that would definitely be something that would be useful.
Yeah, I think the first feature I would ask for is more support of the power saving. You know, now the GPUs has some features to allow you to explore the balance between performance and power saving. And the GPU even have power sensors, but I feel like it's not enough, especially considering that the GPU is becoming more and more power hungry, and people pay attention to sustainable computing or something. And maybe allow the programmer to control the voltage of HBM, you know, like what you are doing to control the power consumption of GPU cores. So maybe you can do the same thing for HBM so that you can save the power. Some feature like that, you know, some power saving features. And another feature we are looking for is more flexibility on the memory usage. Just now, you know, the last talk is a very good talk, and the author mentioned that the kind of limitation of this the page movement, you know, I'm thinking that what if the data movement can happen at the cache line level, that of course demands some hardware changes, you know, tracking introducing this cache coherence. That's a lot of changes, but it can significantly reduce those page fault overhead and you know, reduce the data movement overhead. And well, you know, currently Aaron and I are working some project, and we in that project we make a part of the GPU memory working as the hardware managed cache for CPU memory, and we demo the big benefit of doing so. You know, simply leveraging this cache coherence protocol, we manage the data movement. Yeah, so simply speaking, if there's more flexibility to allow the you know, flexible data movement or the memory management, that would be wonderful.
Professor Daniel Wong, you have any opinion?
Yeah, I would actually agree with Wong about more fine-grained power management control. A lot of my research deals with that, and we run into that limitations. You know, on CPUs, you have very granular control over like per core DVFS and sleep states. Sometimes we see opportunities with that for GPUs. I'm sure for the overclocking and gaming community, that'll be fun to tweak with too as well if we could have those type of features. You know, and then you know, the other nice feature to have is always more memory, right? We always need more memory on GPUs for larger workloads. So yeah, those would kind of be on my wish list.
Okay, on my wish list, I would say I probably sometimes really want some new program models. For example, right now it's still the CPU style, like load data, process data, and store data back. But actually, we see the data being processed in pipelines, like data needs to go through a few stages and getting stored back. Can we have some new program model that, or like it definitely need hardware changes so that we can program in a pipeline style or in a style that I cannot even imagine. That's something I really expect that GPU can happen. But even if something is introduced, it's a problem if still called a GPU or not. It's probably called CGRA or something else. But I really want to include some new GPU, new hardware feature into GPU.
Actually, just to comment on a couple people mentioned fine-grained power management. We actually have a paper in NASPLOS in a couple months on this very topic. Yeah, there's a lot of opportunities, especially when you start considering the fact that GPUs have really long memory latencies. So there, you know, if you can adjust your frequency and power at a very fine granularity, you can really take advantage of potentially, you know, a lot of threads being stalled on memory at any point in time.
What about sparsity?
Sparsity? Is there any panel to opinion about sparsity?
Well, so today, right, NVIDIA has, you know, 2 to 4 sparsity. How many people use it? Okay, one person here is there.
So I also want to add that say sparsity probably can be handled at part of the memory hierarchy, that you can remove the zeros out of the just from the while we're loading the data from the memory. So it really, let's say, if you want to handle sparsity well, you probably need the new program models. That's my opinion.
You have a question?
Oh, well, I was raising my hand for I use 2-4 sparsity, but I actually have like kind of a follow-on, which is just like, you know, so we mentioned tensor cores, like, you know, obviously this is all about neural networks. As these, you know, we get higher or like really lower levels of quantization, like what about like trig computation or like, you know, 2-bit arithmetic, or, and like on the other hand, what about like native compression in hardware or decompression, really? You see where I'm going with this?
Thanks for sharing all your insight on future GPU workload.
Well, I mean, I'll just quickly, I mean, so I mean, it's, you know, compression in GPU caches has been done, you know, mainly in NVIDIA GPUs for multiple generations for graphics. So it's not a new concept.
I'd like to add, yeah.
No, go ahead.
Sorry. I'd like to add one more comment to handle this sparsity. You know, one thing we could do is ask for more memory bandwidth. Now the problem is that the interconnect like the CXL, if that's highly integrated into the GPU, then you can have, in theory, unlimited memory bandwidth to serve your memory request and to serve your sparsity memory request. But of course, now the NVIDIA interconnect is closed out. I don't know whether it will support CXL memory. But if that's possible, then we will at least have more abundant memory bandwidth to serve this sparsity.
So just let me say, AMD, we have we're fully open sourced in our graphics. So.
Good job.
This is not related to sparsity, but do the discussion, we expected some ML related answers, but not much. That's great. But if we speak about the ML, then what do you think? The NVIDIA GPU has some. It is actually a general purpose GPU, but it has its own specialized core, which is tensor core. The tensor core is best majority time idle if we run not non-ML application. Do you think that is the ultimate solution that we can do, or is there any more fundamental architectural revision that we can do for supporting emerging application in the future?
I mean, I'll give another quick answer there, but I mean, yeah, so the problem with tensor cores, right, is that it's really hard for a compiler to target, right? So yeah, if you can actually target an accelerator using some sort of automated framework, or a compiler can do it, I think there's a lot broader acceptance than you have to use a specific library to target an accelerator.
I just also think it's sort of a philosophical answer, issue in the sense that do you want it to be a little more general purpose or do you want it to be more domain specific? And I think that's sort of driven by the market, and in terms of the application as well. So I think it's still sort of an open-ended question in terms of which direction is the right way to head.
I just want to follow up another question. So for John and Brad, do you think that some company like NVIDIA or AMD, is that possible if they have two product line that one is being more general, one being more specific on some particular applications?
Well, I mean, you see this today, right? We have two different GPUs, one for graphics and one for compute, right? They're RDNA architecture and CDNA. So I mean, there's already bifurcation right there for the market. So then folks know, their Xbox and PS5s, right? Those are also AMD specific graphics, but those are for particular markets as well. So yeah, I think it's already very much a customized solution.
We asked about what new features we expect to see, and the graphics computing pipeline has driven like the architecture of a GPU, and now these machine learning models have the additional architecture and feature implementations. Which new application or which new workload do you think will drive the next set of features?
For example, just to have an example, what about, for example, security issues from multi-encryption, for example?
Well, so I think people are seeing ML as just the rocket ship's just taking off, right? So like, I don't think too many people are thinking about what's next as much as trying to ride the current ship we're on. But I do think, making it cheaper by allowing multiple users of the same system in the cloud, right? And those features that enable multi-tenancy to be better, right? And quality of service in that kind of situation, as well as security and privacy. I mean, those are all very valuable.
Is there any question or?
What do either of panels think about wafer scale and domain specific accelerators?
Yifan, I think a lot to comment on that.
So wafer scale multi-GPU system. So I think at least at this stage, it's more like a concept than a possible product. It still probably need many years to get mature. I think we actually have I have one student dedicated to this direction that we're doing some early stage exploration. We find out that if we want to make it useful and sell one wafer as one product, many things need to be changed. The program model doesn't really work. You cannot use a whole wafer to just calculate one matrix multiplication. It's the utilization is super low. The data movement is terrible unless you use optical communication. So there are lots of things to research before it can really be exploited. But I think it's a very interesting direction because it's goes beyond the traditional like 4 chiplet multi MCM GPU design. So is introducing lots of interesting problem to solve. So I think for academia, this is definitely interesting problem to explore. And for product, it still takes some time until it can be commercialized.
So this is a company called Cerebras. Who was talking there?
Yeah, Professor Yifan.
Yifan, there's a company called Cerebras. They have been there doing wafer scale engineering, like 2nd generation now.
Yeah, in terms of Cerebras, I think their work, I wouldn't call their GPUs, their say a specialized CGRA or some type of course. I think overall the direction is very interesting. Then even without a wafer scale, you just produce something like that with a lot of cores, with a big mesh, and then with a programmable like processing elements. It's actually very interesting. I think right now their market is more like for research and DOE customers. I think it still also takes some time becoming really popular, and the cost is another problem.
I probably asked the question, but I think the key thing is that current multi-GPUs are pretty good. They are able to build them out, and NVIDIA with their NVLinks are pretty powerful in terms of the amount of bandwidth they could generate. The wafer scale, I think, provides a different substrate, and if it can provide something that current multi-GPUs cannot, I think that's where you would see maybe a little more traction. For example, I know one of the biggest issues, at least with NVIDIA GPUs, is in terms of scalability, is reliability. They can't really scale out at those given bandwidth to the number of GPUs they want because of reliability concerns. But if you could build something on top of wafer scale, provided with bandwidth that's almost free, for example, if you have optics or something, and you could sort of address the reliability issues, maybe that's a game changer. So I don't think it's going to be sort of the incremental. It would have to be some sort of a shift in sort of some benefits you can provide, but I think that still needs to be determined.
I'm new to this field, and but the current GPUs, for example, used in neural network are the incremental changes from graphics and gaming, and so now some GPUs are generated that don't have like some something like that. So are current GPU designs for like neural networks, do they still have legacy from the graphics and gaming times? Or, I mean, if they were done now, would they be done differently? Or are there things that are still stuck in some legacies that you want to be changed? Is it clear?
I'll answer that first, and others can join in. Yeah, GPUs are fundamentally, even before they got into machine learning, they were accelerators for matrix multiply, right? And they were very fortunate that, you know, ML basically needs the same core operations done that graphics does. So I think, you know, that's persistent no matter if they're being optimized for graphics or ML. I mean, as I mentioned earlier, right, there's already two different versions of our GPUs, you know, for different markets. And I mean, you can look at our ISAs, they're open. You can do a comparison between the two and see, well, there's some common instructions between both CDNA and RDNA, and there's a lot of instructions that are only in RDNA that don't exist in CDNA. And there's a few in the other direction as well. So yeah, I think, you know, the market is so big for ML that, you know, people would do whatever they could to accelerate ML and get a bigger market share. Yeah, I don't think there's anything that is kind of legacy in one architecture that you wouldn't do it now just because the market's so big.
I think if I could answer that question in a different way, if you were to redesign the architecture for ML, not graphics, I think the architecture would look different. I could say this with a little bit of confidence because I spent a summer at NVIDIA several years ago, looked at the details. We looked at some of the architecture components, but there's a lot of junk in there. Junk is not the right word. There's a lot of mess in there that exists because of GPUs.
Give some examples.
I don't want to talk about that. There's a lot. So I'll give you an example of what I looked at. So I looked at a lot of the interconnection network stuff. I looked at the on-chip networks. It was very non-pretty because of, again, there was just a lot of graphics components. And some of the architectural changes that we as a researcher would look at are not really feasible because of what goes on in the real GPU architecture. So there are quite a bit of differences. I think some of that comes from because it was a graphics processor, not a GPGPU. So it would be an interesting thing to sort of think about if everything was designed from scratch. It might be different, but I think that's still an open topic.
Well, just one comment though. I mean, it is a lot of work to get out a high production chip, right? And so you have to make incremental changes. So I think, yeah, some of that what you're seeing is very much there is legacy just because you can only make so much in one generation. But I don't think there's a feature that we would want in ML that wouldn't get into the next architecture if you could justify it.
Maybe last question.
There were some mentions about programming model, and then you guys talked about like making those chips bigger and maybe having multi-chip like GPUs, right? And the programming model has not changed much. We still have the concept of blocks and grids and so on. Do you see a new level of hierarchy put on top of blocks and grids to target those bigger chips? Or maybe like multiple GPUs inside a cluster? I don't know.
I think it's a very plausible. I mean, I certainly can't announce any changes, but I mean, I think what you're saying makes sense personally.
Yeah, I want to add to that. Yeah, if you want to continue programming GPU with CUDA-like programming model, it's just too difficult. And especially if you want to have performance. So you see, the people is always struggle with this high-level program abstract and low-level programming model like CUDA. Now, Triton, you probably heard about Triton from OpenAI, and this is very good initiative to narrow down these gaps between the high-level and the low-level programming method. And I would expect that this kind of effort will continue, and it's not enough. And before Triton, we even have OpenMP, OpenMP, which is another high-level programming model. But once people use OpenMP to program CUDA, they still find a very big performance gap. That's why we have this industry effort like Triton to continue the effort of narrowing down this gap. And I would say that in the near future, we probably will see something more work to narrow down this gap, maybe with the help of machine learning. Yeah, we have this machine learning generated code, very, very efficient and very high performance. So that may be a way to narrow down the gap, but I would say this is an ongoing effort. Yeah.
So just to answer that question, NVIDIA has already added another hierarchy of cluster for the distributed shared memory. So it's already in the works. So I don't know if we need higher levels of hierarchy more than that, but with the algorithm demands, we probably need to go up further. Yeah.
Yes. So due to the time limit, so now it's to move on next question. So thank you for sharing your insight on future hardware and component features. So now shifting our focus toward availability of latest GPUs and collaboration with industry. We all know GPUs are really important to non-many critical applications. So but however, the cost of GPUs are really highly increasing at the same time. So many researchers have trouble getting some more recent GPUs. So our second question is, how do you think academia can compete or collaborate with industry? Is there any opinion for?
Well, I think all these questions. Please. I don't mean that. I mean all the time. So I mean, I think just the cost of GPUs right now is just supply and demand. As I mentioned earlier, right? The ML market is just so big. I mean, what NVIDIA announced their margins on for the latest quarter is 70%. I mean, that's just unheard of in the industry before. So I mean, I think we're just at a point where there's just so much demand, so much thirst for that throughput that it's just going to be hard. I do point out that there's been some great work that some of us in AMD have done, especially on the classic Xilinx side with their university programs. So they've created these what they call hack clusters which are instead of trying to, give one or two, FPGA boards to a bunch of universities. They've created clusters of 64 or 128 FPGAs in 5 different universities, I believe, 2 in Europe, 2 in the US, and 1 in Asia. And those actual clusters actually not only have FPGAs now, they do have actually GPUs as well. And so, consolidation, right, of, hey, let's work with an industry partner and try to create a single residence where, a bunch of researchers can have an account on, I think is a much more viable route than trying to have everybody get their individual local GPUs. I know sometimes you really want to be able to hit the power button locally, but, there are methodologies out there that make it a little easier.
So I have a question to kind of follow up on that. So, a lot of these GPU resources, like you mentioned, these hack clusters, people could, develop applications on them or train neural networks on them. But a lot of people who work on systems like us would need to hack runtimes and drivers and potentially make the system unstable. And if we use older GPUs, reviewers may ask, hey, what about these new GPUs? And we don't have access to that. We can't really break the system and, reset it like we can, So do you have any advice for systems researchers who need to hack the system and break things?
Yeah, I understand it's difficult. I mean, I think it's somewhat not. I think it's hopefully just a very kind of temporary problem. But I mean, yeah, those clusters, as much as they will allow you to adjust them, yeah. But I understand that's not going to help everybody. So
Great. Yeah, thanks.
Is there anybody who has any question on this topic?
I think a question with a reviewer asking for the most recent version of the GPUs, like if a reviewer asking me what about if your algorithm runs on H100, I don't really have one H100, and what about why not using that one as a baseline? And sometimes simulation is just super slow. So I would think this is a problem with our reviewing system probably, and also it's better that the academia probably can have a baseline that everyone can work on. That's probably Python's work on creating an open source the Vertex GPU is definitely a solution to this problem. So rather than like chasing the industry, probably academia itself can have some sort of baseline either on the simulator or on real GPU that they can, like the community can build on each other, especially for architecture researchers. So I don't know how likely that our community will accept this approach. I know this approach definitely has its limitations, but I think that's a viable solution.
actually, just to remind you, one more plug. I'm sorry, I feel like I'm up here plugging a bunch of AMD stuff, but I just have to say one more thing. So in terms of if you gaining access to real hardware, even MI300X, right, is almost probably as difficult as an H100. But as folks know, my group has been supporting support of AMD GPU modeling in Gen 5 for about a decade now, or at least 8+ years. And in ISCA, Matt Prem is going to be participating in a tutorial, and our goal is we're going to be supporting MI300X ISA in Gen 5 by June. So at least, from an academic, if you want to at least simulate an MI300X, you could do it by then.
I think the other problem, in addition to not having access to the latest, is people talk about scalability. So if I run something on a 4 or 8 GPU system that we have locally, people ask, well, does it work on 64 or bigger, right? And unfortunately, very few of us have access to it. And it's one of those things you can't even really get access to AWS or something. So that's, I think, another fundamental challenge that I'm not sure how to address that.
It's hard for even us and in the industry, right? At that scale, it's really hard.
Yeah, I just thought I'd share from the perspective as a researcher that I feel like I would appreciate seeing more motivation from works looking at cost effectiveness or power efficiency or that kind of approach, because I feel like I read a lot of papers that are like how we can use 64 GPUs to do this really fast rather than how can you use 1 or 2 GPUs to do this effectively. And I think that could help just more of a culture of like cost effectiveness, cost efficiency within usage of GPUs.
Yeah, I would like to second your comments. Actually, this low accessibility of GPU deeply shaped my research topic. One of my research topic is about how to minimize the usage of GPU to train larger models. So hopefully this is helpful to address this problem, but still we need at least have 1 GPU.
I think that's a very relevant topic. I mean, there's a lot of people pursuing that kind of work, not just in academia, but in industry.
So then I would have a follow-up question. So what are the key factors when we design that kind of large scale simulation? So what do you think what is the very key factors to accurately measure the GPU performance for larger systems like 64 GPU or so? I ask you. Sorry.
Yeah, again, I feel like I'm answering too much, so please, any of the others, feel free to interject. But yeah, just plug for AstraSim. So folks know, Tushar Krishna's group at Georgia Tech, right, has been using AstraSim for several years, open sourced, and it's getting a lot of interest, by our team, by folks at Meta, even I believe NVIDIA, and they've aligned with this new Chakra schema for describing ML applications, so they can, collect the Chakra trace from real hardware, then run it in AstraSim. And yeah, I think that's the methodology to make it practical to simulate, 64 or 128 or even thousands of GPUs.
Thank you very much for sharing your thoughts.
Question.
Okay.
No, I was just, you got the wrong seat when you were sitting down there. No, I was just, I guess I just add a little more to that. I think it's, what is it that you're trying to learn, or what is it you're trying to model? What are you trying to gain when you're doing the simulation? So if you're doing multi-GPUs, you probably don't care about the individual components within the core. Probably care about the communication. So you can model that separately. And if you're just going to model communication, it's pretty easy to do. It's not a difficult task. I think the big challenge is that there's sort of interaction between the communication, the compute, and the memory hierarchy that occurs in a real system that's very difficult to model at scale. And I think those are some of the challenges that you would have to have a full understanding of experience running on a real system, and that's really hard to do. So even in a 4 GPU system, we've seen things where people say, well, you can overlap communication compute. In theory, that's true, but we've seen where it doesn't really help with performance. So those are some of the things that really can't be, that's really difficult to model. And we've looked at AstraSims, and it models the key components of communications, but when you're trying to look at the interaction between the compute, the communication, and then the memory hierarchy that sits in between, that's a little bit challenging, and I don't know if there's a good answer for that.
Yeah, just to say, yeah, AstraSim definitely needs additional modeling features, right, to really, have all those resources. Completely agree with something.
So, in my experience, I work on very low level simulation. I start with low level instruction level simulation. I find if you want to simulate, say, even a single H100 or MI300 GPU, it's already almost impossible for you to, say, simulate an application that can utilize all the compute unit, all the cores for one time. Then it will probably spend the whole day on just running one simulation. So I think we are actually working on projects that trying to rise the level of abstraction, but rise the level of abstraction to what level is actually a question. Generally, the higher level abstraction, the lower accuracy that we can get. But we find it's not necessarily true. So we're trying a few different approaches to avoid modeling at the instruction level, but at a higher level. For example, in one project, we consider everything as a pipeline, then just consider even a cache as a pipeline, a communication channel is a pipeline. So we model the latency and parallelism at every component. Hopefully, we can improve the performance by like 10 to 100 times. Then definitely there are other methods like sampling or just something like AstraSim. We don't really simulate instructions, but rather at the kernel level, using traces measured from real GPU. Those are all methods that can allow us to simulate large scale GPUs. I think if we're going down towards the direction, say we execute one instruction, fetches memory from a remote memory, then go through the network, comes back. I personally think that's a very, very difficult simulation model.
Thank you for your sharing your experience. Due to one last question. It's okay.
Yeah.
Okay.
Yes.
Right. So regarding the bigger system, that do you think that the current synchronization orchestration method is going to be the optimum, or if it's not, what would be the next abstraction?
Synchronization for CVD or
Synchronizing for clusters of GPUs.
So can you be a little more specific? What do you
For example, currently we have collective communication collectives. Right. Then we're trying to overlap compute and communication, right? Because communication collectives are asynchronous in nature. That's why we need all that. To see we just go all async all the way, like just hypotheticals.
Sorry, I can only comment about my own experience, but we've used Nickel, we've analyzed that. It's surprisingly very well optimized, such that the overhead of synchronization is almost negligible. Because you take advantage of the number of threads available, and there's a lot of actually overlap, not the actual main computation itself, but there's compute required. For example, if you're doing all reduce, you need to do compute, you need to do memory copies and so forth. There's a fine-grained level of pipelining that occurs within the implementation. So it's very little desynchronization was exposed, at least based upon our experience. So actually, we haven't scaled this out to a multi-cluster system where you have to go through from an NVLink domain to an InfiniBand domain. So we haven't looked at it in that aspect, but everything that was in a single domain, for example, whether it was a PCI-based or an NVLink-based, synchronization wasn't really a significant issue, at least from a collective communication perspective.
So due to our time limit, these will be our last questions. So do you have any suggestions for the GPGPU workshop? For example, do they consider merging workload domain, or how do you think we can make it better and more useful?
Yifan, we're going to start from you.
Should
go backwards.
Yeah, I'm the audience of this question. There's definitely, all these questions are prepared by we a few people. So, so I'm
This is more for the audience or anyone in general. So these are questions from the organizer.
Sorry, I'll start then. I mean, I don't know the answer, but I think it's interesting because this is HPCA 30th edition. So I was looking at the first HPCA. I was looking at the names of the sessions there. And some of the session names are still valid 30 years later. For example, there was a cache management session. So obviously there's another cache session this year as well. Some of the sessions they were talking about latency reduction in HPCA 1 30 years ago. that's still valid as well. We have 75 papers in HPC this year. I think there was about 6 of them that were really focused on GPUs, so that's about 10%. I think there were about like 25% of the papers are on accelerators. So you could sort of see where things are going. So obviously the core GPU sort of papers are dying down. I think it's just because of people are jumping on different bandwagons. But is there still a place for GPUs? Obviously there is. It's just what is the focus that you want to place in terms of the emphasis? I think GPUs are not going to go away. Right? I don't think anyone would argue with that. I think GPUs, just like CPUs are going to be around. Caches have been around for years, but there's still good cache papers that are being published, but maybe not at the same rate they were being published 10, 15 years ago. So I think the key, at least from the workshop perspective, is what sort of stance do you want to take? Do you want to maybe take on papers that are more traditional, that aren't going to meet the novelty bar of regular conferences, or do you want it to be a little bit more controversial, things that maybe that won't be accepted in the main conference, but maybe could be used as sort of a discussion forum kind of. So maybe just get a bit more, maybe instead of a paper, just sort of a presentation of different ideas, sort of like a work in progress of different approaches people are thinking about that maybe aren't well thought out, but maybe used as a forum for discussion. So that's just sort of a thought. I'll let others talk.
Well, I had some thoughts, I guess, at least I didn't go first this time. So yeah, I think, looking back right from HPCA at the very beginning until now, I mean, one of the things that I feel like really has helped the HPCA is the merger with CGO and PPOP several years ago. It's really, added a lot more attendance, and, for myself, there's definitely capability to kind of move between different, conferences and see different talks. I think, GPGPU, already we have, a lot of compiler expertise attending, these adjacent conferences, but we don't see a lot of compiler kind of discussions here. If we could try to pull some of those compiler, workshop or, kind of new work ideas into this conference by kind of broadening maybe what the topic list of GPU, that could be one. And then the other thing, there's not really a networking conference as part of this, coalition of conferences today. But if we could pull a networking conference in here, I think, GPUs plus networking is just a huge area that would be such an interest to see papers in that space.
Yeah, I have a question. Do you see GPGPU graduating to be a full conference, like in the near future? Because there is like 10% of the HPCA papers that will be published on the GPGPU conference.
I think that's very, very risky in the sense that you would have to have a path forward. The reason I say that is there was a workshop on network on chips 10, 15 years ago that sort of proceeded into a conference. Initially got a lot of support. It's on life support today. I think you would have to have a clear vision in whether you want to focus just on GPGPU or sort of what NVIDIA calls accelerated computing, and then have a vision for that, because you don't want it to be a 2-3 year conference and then sort of die down.
No, NVIDIA has this GPU conference, GTC, right? So I'm thinking maybe, but that's a highly industry oriented, not research oriented. But that could be an example of it. Yeah.
So just talk a little bit about our experience in doing GPGPU, and this is already my third or fourth time doing GPGPU, and we got just lots of good papers, but definitely the paper number is not ideal. We kind of want to have more papers and more and high quality papers, and previous years, we try to just say, okay, if we want 8 talks, we just want 8 papers. But this year, we're kind of really rather strict on the quality of the papers. and rather than having shorter program, then but have good presentations. And also, I find that the workshop paper reviewing process is interesting. It's not as reliable as a regular conference, and it end up with a few chairs that we read carefully with the reviewers' comments and also read the papers and then make the final decision, but not only on the reviewers' recommendation. Now we find is usually some papers are insightful, but maybe the writing quality is limited, but we think that's okay. We can include those papers because that's insightful, right? It's useful to spark a lot of discussion during the workshop. And I think that's something I learned from organizing this workshop. I think definitely I want to have this workshop in a way that is more like a discussion forum, rather than a place to publish papers, like rather than a journal station style. So I don't know, what do you like the idea about, say, next year we can have someone to nominate speakers and then we can invite speakers rather than based on paper. For example, if join us nominates Brad, then we can invite Brad just to give a talk about your recent work and your visions in the future, but rather than a future specific work. And I don't know, what do you think about this idea, now if we can follow this format in the future.
Thanks to all panelists for good suggestion. And I think time is over. So thanks to everyone and who attended to today's panel discussion, and thanks for panelists. Thank you.
Thank you.